Now, with mass spectroscopy, we don't, like I said, we don't get much information. Get the molecular weight, few of the pieces of the structure. But let me talk just a little bit, give you some background information on how it works. It works basically the same as almost any instrument. I talked a little bit in the lecture about UV vis spectroscopy, and mass spec kind of works on that same principle. In UV vis, it's soaking up ultraviolet and visible light. The molecule soaks that up, goes to some excited state. That's basically what's happening with mass spec. Almost every instrument, you start with some ground state, and we apply some type of energy, and it absorbs that energy and goes to some excited state. I'll put a little asterisk there for an excited state. Now, like I said, basically every instrument there is works this way. We're just applying a different energy source and we get different information out. So we can use ultraviolet visible light and we learn about the conjugation in the molecule. We can use infrared and go to an excited state. The same thing infrared does. And we get information about, infrared's all about stretching and bending vibrations of the bonds, so we learn what functional groups we have. We didn't get to do the NMR here today, but NMR uses radio waves for its energy. Mass spec, little bit different, but basically the same. Mass spec, its energy source, we're going to take some molecule, I'll just use M for some molecule, and its energy source is we're going to use an electron beam. Not important, I'll just let you, give you a number here to kind of go for what this is working at. The electron beam operates at 75 electron volts. Is the strength of that beam. And so that electron beam, we're going to have a collision with the molecule. And when that electron beam collides with the molecule, you knock an electron out of the molecule. Now, if you knock an electron out, then you're going to be left with a radical cation. We've lost an electron. Now, I'm going to write this as 2 electrons here. We're hitting it with an electron. We knock an electron out, so that gives us 2 electrons. This is referred to as ionization. We are ionizing the molecule. We go from a neutral to an ion, and we're making a radical cation. Now, from the knowledge that you have in lecture, you know radicals are very, very unstable. Cations are unstable. And as you can imagine, a radical cation is really unstable. So oftentimes these radical cations will break apart, they will fragment, into smaller pieces. So fragmentation, this is just the bonds breaking. We're breaking the molecule apart. So I had a capital M there for our original molecule, and I'm going to use a lowercase to represent it's broken apart into little tiny molecules now, broken into smaller pieces. One way it could break is that if it breaks it like in half or something, one piece could be the cation, and the other piece would be the radical. That makes sense. You started with the radical cation. If it breaks apart, one would be the cation and one would be the radical. It could also break apart and give us another radical cation. Now, if it did that, if it broke apart and one piece was a radical cation, what would the other piece be? If you start with the radical cation, you break apart and you still get a radical cation, what would the other piece be? Nobody? It would be neutral. It'd have to be neutral. because the radical cation stayed here, so that leaves the other one neutral. Okay, so it can break apart and give these different fragments. Now, in our mass spectrometer, we have a detector that will pick up some of these pieces and can identify them based on their mass, but the detector only identifies cations. It must be a cation. So the detector can identify our original radical cation, because it has a plus charge on it. It can identify any of these pieces that have a plus charge, but it cannot see a radical or a neutral. That detector does not even know they're there. The detector, that's important, write that down. The detector only detects cations. It must be a cation for it to detect it. Now I'm going to give you, you don't have to write this down, I'm going to tell you just a little bit about the instrument itself. This is not important, but it's just kind of nice to know a little bit about how it works. A big box represents the instrument. And we will have an inlet where we put our sample. Now the inlet will have a septum on the end of it here. The entire instrument is hooked up to an ultra-high vacuum. It's completely sealed and it's hooked to an ultra-high vacuum pump that pulls that vacuum on it. We're dealing with very high energy species. High energy species means they're going to be very, very reactive. We do not want them reacting with anything because then they become something else. And that we lose all of our information. We're trying to figure out what was our original structure, some of the pieces of it. But if they react with, say, oxygen or carbon dioxide or something like that that's in the air, then they become something else. And we don't want that. So we pull an ultra-high vacuum on the entire instrument, so there's no chance of that molecule finding another molecule to react with. It's just like having it in space or something. There's nothing else in there. It's ultra-high vacuum. So they can't find anything to react with. Now, there's a little septum on the end, so we use a syringe to inject the sample. You dissolve your sample in some solvent, or if it's a liquid, you can just use pure liquid. You don't have to have it dissolved, but if it's a solid, you would dissolve it and just squirt it in. You need very small amount, just a few microliters is all you need. You don't need much at all. Now, when it gets injected, right here where it goes into, there is a heating block that heats this up very, very hot. That heating block is typically about 400 degrees Celsius. So what happens is it vaporizes the molecule and puts it into the gas phase. So now it's a gas, and it's going to float along. We have a filament that provides our electron beam. So electrons, we run electricity through, that's putting electrons out. So you get your electron beam coming down. That's operating at 75 electron volts. Your molecule's in the gas phase, so it's coming through now, and we have our collision. So we knock an electron out of the molecule. So now it's floating along, and now it's a radical cation, or it may start fragmenting into those smaller pieces. We'll have some of those as well. So you may see just a cation or another radical cation fragment. Now, these aren't going to exist for very long. So we have, to speed things up, we have a quadrupole. There's 4 poles. Kind of hard for me to draw this. I had pictures, but I'm going to draw 2 poles there. Trust me, there's 4. It's called a quadrupole. and there's 4 poles, and these poles we can run voltage across those and change the charges of those poles. You can imagine if these poles were positively charged and our molecules come in here, then they will repel each other, and so it shoots those through really quick because they're repelling each other. And so it just happens in just microseconds. It shoots those through there. Now, the other purpose of the poles is as we change the voltage on these, you can imagine these pieces coming through. The smaller pieces, being lighter, being smaller, they don't weigh as much, they're going to shoot through much faster. Your bigger pieces, huge big old pieces of the molecule, or maybe the original molecule where all we did was lose an electron, much heavier, they're going to move through at a slower pace. Now it's still fast, but it's slower than the small pieces. So when they come through and they hit a detector, based on when they hit the detector, that detector will know the mass of it. And so that detector can measure the exact mass. It can measure it out, depending on the instrument, it can measure to several decimal places. We have 2 types of mass spectrometer. There's a low resolution mass spectrometer that only measures it to 1 decimal place, and then there's a high res mass spec, high resolution, that will measure it to 4 decimal places. If you use the high res and go to 4 decimal places, you will know the exact formula for your molecule. Not only do you know the molecular weight, you'll know the exact formula. You'll know it's C6H5O or something like that. You'll know the exact formula if you go to 4 decimal places. There's charts and charts you can look it up in and find the formula if you know the exact mass. Now, those instruments are extremely expensive. You're talking about minimum $500,000 for one of those. So we don't have one of those. Not that many people have the high-res mass spec. Your big schools will, but your smaller schools are not going to have that. The low-res is perfectly good. The low-resolution mass spectrometer will give you the molecular weight. You'll still know your molecular weight. You just don't know the exact formula for your molecule. But you do know the molecular weight, and you'll know a few of the pieces of the structure. Now, all of this is hooked up to a computer, so your computer reads out a spectrum, and so that's kind of how the instrument works a little bit. Now, what a typical spectrum looks like that you get out. On the x-axis, this is m over z, where m stands for mass and z stands for charge. Now remember, we can only see these charged species, these cations. Normally, most of the pieces that we deal with are going to be a single plus charge, just one cation in the molecule. So normally we're dividing by 1 because there's 1 plus charge. Occasionally you'll make a dication or a trication. If it's a dication, it would be dividing by 2. So the mass you would see in the spectrum would actually be half of what it really is. It may show up at 50, but really it really weighs 100 because it's being divided by the charge. But that's very rare. For our purposes, we're only going to have a mass of plus 1, so we're dividing by 1 all the time. No big deal. So the mass you see is the real mass. We're not going to deal with any dications or trications. They are extremely rare. On the y-axis is percent base peak. Is what we have on the y-axis. Now it may be listed as relative intensity. as well. I may say relative intensity. I looked at some of the spectra. They called it relative intensity. But essentially, it's the percentage of the base peak. The base peak is just the biggest peak in the spectrum. So we're going to have all these different peaks. Maybe something like this. You've got all these different peaks, and on this x-axis is going to have numbers. It's the masses that things weigh. Maybe this is 20, and maybe, I don't know, I'll just put something there. You'll have all your masses. And your base peak is just the biggest one. That's the base peak, the biggest one. The one that is the furthest to the right, the furthest highest numbered one, that normally corresponds to your molecular weight. This is called the molecular ion. And it equals the molecular weight of the molecule. So that is the piece where all we did was knock an electron out. An electron doesn't weigh anything hardly. So all we did was knock an electron out. So it's still, everything else is still intact, and that's our molecular ion, and it corresponds to the molecular weight of the molecule. And then all these other peaks is where the molecule's broken apart and fragmented. Okay, so, and again, the y-axis was a percentage of the base peak. So this would be 100%. And, like this one here, maybe I can't see there. Maybe that's 70%. It doesn't matter. But it's just a percentage of the base peak. It's just relative to that base peak. Let's talk about the fragmentation. Now, before I talk about fragmentation, I want to quickly review. We did this in lecture just last Friday. Let's review real quick stability of carbocations, because we're dealing with carbocations here. That's what our detector picks up is carbocations. So let's review stability of carbocations. A tertiary cation is more stable. Let's put it here. More stable than a secondary carbocation. Secondary is more stable than a primary carbocation. Primary is more stable than a vanillic cation. That's where it's on a double bond, plus charge on the double bond, and also a phenyl. These two are about the same stability. Phenyl cations, where you have to plus charge on the phenyl ring. And then this is more stable than a methyl cation, which does not exist. Now, we talked about resonance with cations. Resonance bumps you up one spot. So about the same as a secondary cation would be a primary with resonance. If you have a secondary with resonance, it's going to be up here about the same as a tertiary. And then, of course, if you had a tertiary with resonance, that would be the most stable. So resonance bumps you up one spot as far as stability goes. So that's all we care about, is trying to get to a more stable cation. That's what's going to happen in the mass spectrometer. When things break apart, when our original molecular ion breaks apart, it wants to try to break apart and give a more stable carbocation. So we're going to look at some rules and my set of rules that I'm going to write up here is a little bit different than what I have in the slides. So again, I do have a full set of slides on all of this on Moodle. But my list here is just slightly different. So the way the molecule wants to break apart, is that we're always going to try to go to a more stable carbocation. That's what you need to remember. Remember that. All these rules are going to be based on that. We're always trying to get to a more stable carbocation. Our first rule deals with big long chains. If you have big long chain in a molecule, long chains will tend to break at a branching point. So let me show you what I'm talking about. We'll use this as my example. Now, if we inject this molecule into the spectrometer, it will collide with the electron beam. We'll knock an electron out. I don't know where it comes from. We just knock an electron out from somewhere. And so this will now be a radical cation. So I'm just going to put it out here as brackets out there. I'm not drawing the full brackets around. I just drew the corner bracket there. And it's a radical cation. Now, this will want to break apart. It will fragment. Now, our rule says we want to break at a branching point. This is a branching point. You're going along the road, and you get to this place, and then there's a fork in the road. And you got to decide which way to go. That's a branching point. So right there is the branching point. So our rule says you want to break at the branching point. Now it doesn't say which side. We just got a branching point. Which side do you break? Well, it could break on any of the sides. I could break it, there's my branching point, I could break here. On the left side of the branching point. If you do that, then this is our two pieces that we get. Now remember, we started with the radical cation. Most of these, when they fragment, majority of the time when you fragment, one piece becomes the radical and one becomes the cation. That's the way most. I did show you could break one of these apart and get a neutral and a radical cation, but that's not as common. Normally when they break, one becomes the radical and one becomes the cation. So we broke this bond right here. Let me just highlight those carbons. It's this carbon-carbon bond that we broke. And one's going to be the radical and one's going to be the cation. Now which one's going to be the cation?
The larger one, because it's going to be more stable.
Exactly. You were listening to me. Somebody's listening. I said all that matters is the stability of the cation. If I put the cation here, it'd be primary. If I put it here, it's secondary. I want that secondary. That's more stable. So that's where the cation is going to go. The other one would be the radical. By the way, before I forget it, in our mass spectrometer, things are moving through so fast in the mass spectrometer that normally the molecules do not have time to rearrange. So we don't do cation rearrangement in the mass spectrometer. We're shooting them through just in milliseconds or something, or microseconds. We're shooting them through very quickly, so they don't have time to normally rearrange. So the bond breaks, there's the cation, and it just stays right there. Now, go back to our branching point. I could have fragmented here. The rule just says break at the branching point. I could break off the methyl group. Okay, so we broke the methyl, and there I highlighted the carbon that's here, the branching point carbon. So one of these is going to be the radical, one's going to be the cation. Which one's which? Which one's the cation?
The larger.
I'm sorry?
The larger.
That larger one, this is the cation. Because we just said in our list there, methyl cations don't even exist. So this has methyl has to be the radical, because the methyl cation doesn't exist. Now, got one more place. I could have broken here, on the right side of that branching point. So I broke that bond. Again, one will be the radical, one will be the cation. We want the more stable cation, so it's going to go here, and this one will be the radical. Now, which one happens? Which way does it like to go? All of those will happen. All of these will take place. We will see, remember, only the cations show up. You get a peak for the mass of every cation. So this one will show up. That's our molecular ion. That's where all we did was knock an electron out. So I'll see a peak for that. I will see a peak for this cation. I will see a peak for this cation. And we see a peak for this cation. Whoops, sorry. I circled wrong. I got carried away there, didn't I? Peak for that cation. Only the cations show up. So I will see a peak for all of those cations. All of those will show up. Whatever those weigh. You can add them up if you need to see how much they weigh. So like this one's got 4 carbons. Carbon weighs 12, so that's 48. And then however many hydrogens you got 3, 6, 7, 8, 9, 48, 9, 57. That weighs 57. I'll see a peak at 57 mass units because that's what that weighs. You take the mass of all the elements there. That's what that weighs, and you'll see a peak there. And the same thing with the others. You see a peak for all of those masses. Okay, questions about my first rule? Let's look at rule number 2. Rule 2 deals with alkenes. I'm not going to finish it. I'm going to wait and let you tell me first. If I just write the whole rule up, then that's no fun. Alkenes cleave to give something. I'm not going to write what it is yet. Let's look at an alkene. And you're going to tell me where it likes to cleave. Now, we take that molecule, inject it in the spectrometer, it collides with an electron beam, we knock an electron out, we make a radical cation. And that's our molecular ion. Also called parent ion, by the way. I forgot to mention that. Molecular ion or parent ion. I always call it molecular ion, but some people call it parent. But it's going to want to break apart. It will fragment. Now, where is it going to fragment? Would it like to break the double bond in two? Or would you like to break it here? If it breaks it here, you'd have a cation here or a cation here. Or we could break it here, you'd have a cation here or a cation here. Or we could break that one, and one of those would be a cation. Any thoughts on what it might like to, where it might like to break? Remember, everything wants to break to give a more stable cation. So what's a good stable cation that involves a double bond somewhere?
Would you break it the second single bond coming from the double, not that one, the next one, so that it could be resonance off of it?
Yeah. What do we call that cation?
A vanillic cation?
Allylic. Vanillic is where you're... Okay, so this is vanillic. Your cation is on the carbon of a double bond. That's a vanillic. That's very unstable. This is an allyl cation, or allylic. So we break there, and then the other piece will be the radical. So, alkenes cleave to give allyl cations. Because allyl cations are very stable because they have resonance. So they like to, any alkene likes to cleave to give an allyl cation. So find the double bond, go out one more carbon, and then cleave right past that. This is referred to as the allylic position. The carbon next to the double bond is the allylic position. You want to cleave right past the allylic position so that you get an allyl cation. Questions on that? Our next one deals with rings. Rings are resistant to cleavage. We don't like to break a ring apart. Rings are very, very stable. For most rings, we like to cleave right next to the ring. Now there is an exception to that, and we'll deal with that in just a moment. So we normally, most rings, we like to cleave right next to the ring. So let's look at an example, some examples of that. Here's an example of a molecule that's got a ring. So if we take that molecule, inject it in the spectrometer, it collides an electron beam, we knock an electron out, we make a radical cation. Then it's going to fragment. When it fragments, what this says is we like to break it right next to the ring. You don't want to break the ring apart. You want to leave the ring together, but we want to break it right next to the ring. Because that will give us a more stable cation. This one will be the cation, the other piece will be the radical. So they like to break right next to the ring. That is kind of like the first rule, because if you look at it, that's kind of like a branching point right there. There you can see it's branching off. It's just that all this rule is says we got to break it on the outside of the ring. You got to break it on that side of the branching point, you know. But essentially, that's a branching point. So kind of related to that first rule. Now, the only exception to breaking right next to the ring is if we have an aromatic phenyl ring. We haven't learned aromatic yet, but phenyl is an aromatic. We learned that term last semester. But so far, the only aromatic compound that we've had is the phenyl ring. Now, if we take a molecule that has a phenyl ring in it, they're a little bit different. We inject the spectrometer, knock an electron out, make a radical cation. But when it fragments, so all your other rings want to break right next to the ring. But if we break right next to it on here, we make a phenyl cation, which is very unstable. So they like to break, kind of like those alkenes did. They want to go out one more carbon and then break. Because that gives us something that has resonance. So if I break there, that gives us this cation. This is called a benzylic cation. We haven't learned that yet. We will very soon in lecture, but it's called a benzylic cation. Very similar to the allylic cation with the alkene. That cation has got resonance with the phenyl ring. This is a phenyl cation, don't confuse them. Phenyl cation has no resonance. That cation has no resonance because it's on the double bond. It has no resonance. That cation sits in an sp2 orbital. That cation sits in a p orbital. You have to be in p orbitals to do resonance. So we can do resonance here. So with the phenyl rings, you want to go one carbon out and then cleave. That makes a benzylic cation. This is called the benzylic carbon, the benzylic position. Just like we had the allylic, you had the carbon next to a double bond was the allylic position. Okay, so that's how rings like to do. Most rings, we want to cleave right next to it. Phenyl rings, you want to go one carbon and then cleave. Questions? Okay, our next rule deals with molecules that contain a heteroatom. What are our heteroatoms? Anybody remember heteroatoms? Which ones are called heteroatoms? You don't have to give me all of them. Can you give me one or two?
Nitrogen.
Nitrogen's the heteroatom. Another one?
Oxygen.
Oxygen. Any more? You're doing good.
Sulfur.
Sulfur. One more. So you did nitrogen, oxygen, sulfur. So oxygen and sulfur is about the same. What's my last one then? Which one's phosphorus? Thank you. It's right under the nitrogen, so it's very similar to the nitrogen. Your heteroatoms are the atoms that have lone pairs on them. That's your heteroatoms. They have a lone pair. So molecules with heteroatoms like to cleave the carbon-carbon bond closest to the heteroatom, next to the heteroatom. So a heteroatom is something that has lone pairs. So I'll show my lone pairs. That oxygen is a heteroatom. It has lone pairs. So what this rule says, okay, first we're going to inject the molecule into the spectrometer. It collides the electron beam. You knock an electron out, we generate a radical cation. That's our molecular ion or our parent ion. We will see a mass for that. But then this likes to fragment, and it wants to break at the carbon-carbon bond that's closest to the heteroatom. This molecule is symmetrical, so it doesn't matter which side you break. If it wasn't, it'll happen on both sides if it's not symmetrical. But here's the closest carbon-carbon bond that we have that's next to the heteroatom, so it likes to cleave right there. Now one of these pieces is going to be the cation, one's going to be the radical. If you put the cation here, it's a primary cation. If you put the cation here, it's primary carbocation. Does it matter which place it goes? Yep. Which where is it going to go?
You want the oxygen.
Why?
Resonance.
Yes. So this one's going to be the radical, this one's going to be the cation. And remember, there's lone pairs on that oxygen. So it likes to go there because we can draw resonance for that. You've got resonance to stabilize. See, it's got resonance. So that's a more stable carbocation. Resonance bumps you up one spot. And although it's primary, it's going to be just as stable as a secondary because it's got that resonance. So with the heteroatoms, if you have any of those heteroatoms, because they have lone pairs, you want the carbon-carbon, break the carbon-carbon bond that is the closest to that heteroatom so that that cation can be on the carbon next to the heteroatom. That gives me the resonance. Okay, one more rule. Now, in my slides that I have on the Moodle there, they've got more rules than I've got more rules listed than what I'm doing, but it just kind of split some of these out. They say the same thing, but they kind of divided some of the stuff up a little bit more. Okay, so our next rule says that elimination of small stable molecules is favored. What do I mean by small stable molecule? Things like carbon monoxide, carbon dioxide, a nitrogen molecule, a water molecule. That's stable. Hydrogen sulfide. Hydrogen sulfide, just like water, it's just a sulfur instead of oxygen. Maybe some small alcohols sometimes. Not anything too big, but sometimes you can eliminate a small alcohol. Okay, so those are some, I'll just leave it there. There are others, but those are probably our most common. Okay, so those are some small, I'll put one more. Sometimes we eliminate ethane. Ethane's nice and stable. Sometimes it will eliminate an ethane molecule. So let's look at an example of one of these. Let's take this one. So we inject this into the spectrometer. It collides with the electron beam, makes a radical cation. That's our molecular ion or our parent ion. This will want to fragment. Now we already dealt with this earlier. So one place it can break is the carbon-carbon bond closest to the heteroatom. We just had that rule. There's our heteroatom. Here's our carbon-carbon bond next to the heteroatom. So one thing it can do is cleave right there. And it's going to do that. And that will give us those pieces. So we will see a peak for that cation. Remember, radicals don't show up. We don't see peaks for radicals. We only see peaks for cations. But the other thing this can do, it can, instead of fragmenting like that, it can eliminate a small stable molecule. So this is the other thing it can do. I'll put it in a different color here. It can take a beta hydrogen. This is our alpha position. Here's beta. We learned last semester about beta eliminations. That was like our E2 eliminations, E1 eliminations. Those are beta eliminations. If I pull a water molecule out, take a hydrogen, a beta hydrogen, and the OH, that makes a water molecule. And then the rest of this is going to become right here between the alpha and the beta position. If you pull this out, this will be an alkene. Now, we've got to deal with our radical and our cation. Where's our radical and where's our cation? Okay, I'm going to put it out here in brackets because I don't know where it's at. But yes, there will be a radical here. Now, where's the cation?
H2O is small stable.
Okay. So where's our cation? We had started with the radical cation. We've still got a cation somewhere.
Is that going to fragment again? This one?
It might. That's a possibility. But where's the cation to start with? Is cation on water? No, water's neutral. If it's not, we're all going to die really quick. So the cation's here. That's a radical cation. So this one broke apart. When you eliminate these neutral molecules, remember I said back earlier, things can fragment to give a cation and a radical, or they can fragment to give a neutral and another radical cation. So this one fragmented to give a neutral and another radical cation. Okay, so that's another way, and these work basically the same. You can eliminate these out in the same type of fashion. Okay, so that's the way things like to fragment. Now, we're going to go through some examples, and I'm going to try to draw these spectra up. So this is what you have in your handout. You have the real spectra, so please give me a break on my drawing abilities here. I'm going to try to scribble some of these up. I'm probably not going to draw up every single peak that's on your spectrum, but I'll draw the more important ones. So I've got some real examples here. So our first one here is 2-methylpentane. We inject that into the spectrometer. It collides with the electron beam. We knock an electron out. We make a radical cation. I should have a peak for that cation. That is our molecular ion or our parent ion. And that had a molecular weight of 86. And if you look at that spectrum, down there at 86, there is a little tiny peak. That's at 86 if you look down there, all the way over there to the right. There is a little peak. That's our 86. That's our molecular ion. Now, I know this is weird, but most people just show it with a capital M and a plus charge. Technically, it's a radical cation, but most people don't bother showing the radical. They just show it as a cation. So that's our molecular ion or our parent ion. And you can see that molecular ion or a parent ion, it corresponds to the molecular weight of the molecule. Our molecular weight for the molecule was 86, and we got the peak there at 86. So even if it was an unknown compound that you were doing a mass spec of, you will know its molecular weight. Now, this will want to fragment, and that's what's going to give rise to all the other peaks, is where it fragments. We'll have the one peak that corresponds to the molecular ion or parent ion. It's always typically the furthest one to the right, or the furthest big one to the right. We'll talk about that a little bit. There are some things that can be a little bit further. There is a, let's see what we can identify. Now, in a mass spectrum, you're not going to identify every peak in there. There's no way. I don't care how good you are. You're not going to be able to figure out every peak in there. Because we're dealing with some very high energy species. There's a lot of weird things that can happen. But you should be able to identify the big peaks. The biggest peaks, that means the bigger the peak, the more abundant is that species. And it's following the rules, because that's leading to something very, very stable. So your biggest peak is the ones that's following the rules, and that you should be able to identify. Now, there's a pretty good size peak at 71. A little 70 peak on the side. We'll talk about that in a moment. But there's a 71 there. Now, can we figure out what the 71 peak is? If you'll take the difference here, that is the loss of 15 mass units. I have lost 15 mass units. Does that make sense with our rules? Now, 15 mass units, let's see, carbon weighs 12, hydrogen weighs 1. So if you got a carbon, 12, and hydrogens that weigh 1, that's a methyl group. I lost a methyl radical. Now, does that make sense with our structure? If we break at the branching point, if we can break off here, the branching point. Our rule said to break at a branching point. If you break off a methyl and lose that, then the rest of that would be the peak at 71. That cation is the peak at 71. It broke right here according to our rules. We lost the methyl radical, and that gives us this cation, and that's the peak at 71. Now, it would be nice if you had a list of some of these masses and what do they correspond to. Now, you can add them up like I did there. Carbon weighs 12, you know that off the periodic table, and hydrogen weighs 1, and you could figure out what 15 is if you had to. But I'm going to give you a little list, wherever I've got it here, of some common fragments. And we'll come back to the spectrum here. So some common fragments that we lose, common losses. Loss of 15 mass units is a methyl radical. You're losing a methyl radical. A loss of 18, you often see that. Loss of 18 is a neutral water molecule. Oxygen 16, hydrogen is 1 apiece, so that makes 18 mass units. Loss of 28 is pretty common. 28 is neutral carbon monoxide. Loss of 29 is very common. 29 is an ethyl radical. Losing an ethyl radical. Loss of 31 is common. This is a methoxy radical. Losing a methoxy radical. Let's do a 43. Loss of 43. That is a propyl radical. Now I'm not going. It could be that radical could be on the end. Since you got a propyl group, you got 3 carbons. It could be on the end carbon. It could be on the central carbon. So I'm just going to write this as C3H7. That's a propyl radical. Loss of 44 is pretty common. That's a neutral carbon dioxide. 45 is an ethoxy group. (46) a nitro radical. Nitro group coming off as a radical. And finally, I'll do one more, 57. That's a butyl radical. Now again, I'm just going to write this as C4H9 because that radical could be on different carbons there. That's a butyl radical. Okay, so that's some common losses. And if you'll learn those, they'll really help you about interpreting the spectrum. Now, let's see what else we have here. Not too big, but we do have a peak. Let's see, it's 60, 59, 57. We do have a little 57. It's decent size. We can probably figure that one out. Oh, there's my good notes. 57, that's the loss of 29 mass units. So from the 86 down to 57, I've lost 29 mass units. We know what 29 is. That's an ethyl radical. So I lost an ethyl radical. The peak at 57, now, where do we lose an ethyl group? Right here is the only place we could get the ethyl. CH3, CH2, and then break. Then you lose an ethyl radical. So the peak at 57, the cation would have to be here. This is a cation. Now wait a minute. That is not where it's supposed to break. That is not following the rules. Not everything follows the rules, but that's why it's a small peak. That's why it wasn't very big. Your biggest peaks are following the rules. So I went ahead and pointed this one out on purpose because you might be able to figure a few of these out, but you're not going to figure out every peak in the spectrum. You know, this one doesn't make sense. That's not following the rules. You might be able to figure it out like we did there. But your bigger peaks, you should be able to figure those out. So I'm not going to expect you to be able to identify every peak in the spectrum. Like on the exam, I might say, you know, tell me what the 2 biggest peaks are. Something like that. You should be able to do that. You should be able to identify the 2 largest peaks. Now, let's see what else we can pick out here. The biggest peak that we have is at 43. That's the biggest one. That's our base peak. Your base peak is the biggest one. And if it's the biggest peak, it better follow the rules. Your biggest one is always going to follow the rules. So, let's see what we have. Going from 86 down to 43. That's the loss of 43. We're losing 43 mass units. 43 is a propyl group. We're losing a propyl radical. And if you look at our structure, if we break here next to the branching point, here on this side of the branching point, we're breaking off a propyl radical. That makes sense. So we lost this propyl radical. So the peak at 43 would be this cation. I broke it right here. This side would be the cation, and this side would be the radical. So this peak at 43 is this cation, and we lost the radical. We don't see it. Okay, so we figured out all the biggest peaks there. Now, if you notice on these peaks, on these larger peaks at least, on about all of these, there is another peak on, some of them are pretty good sized, right to the left, 1 mass unit lower. So if you notice, here was a 70, a 71, and there is a 70. Here's 57, there's a 56, you got a 43, and there's a 42. You've got a decent sized peak that's 1 mass unit lower. What would that be? What weighs 1 mass unit? Hydrogen. This is where this, the 71 peak, lost a hydrogen somewhere. It lost a proton. So it lost a hydrogen somewhere, now it weighs 70. This one lost a hydrogen, now it weighs 56. This one lost a hydrogen, this 43 lost a hydrogen, now it weighs 42. So when you see these peaks on the side, this is where it's losing hydrogen. You may even have another one. Like that 43's got a 42, it's also got a 41 here on the side. It's lost 2 hydrogens. So these to the left are where you're losing hydrogens. Anytime you're going to the left here, these are losing, I'll write it here, little arrows going. You're losing a hydrogen atom. And that's always when you're going to the left here. Questions? Okay, let's look at our next spectrum. So next we have 2,4-dimethylhexane. We inject that in the spectrometer, collides the electron beam, we knock an electron out, we make a radical cation. That is our molecular ion, that's our parent ion. We should have a peak that corresponds to the mass of that. That would be our molecular weight. That weighs 114. And if you look, there is a little tiny, boy it's little, but there is a little peak up there at 114. That's our molecular ion, our parent ion. That's the 114. It's small, but it's there. Now, let's see what else we can pick out here. There was a pretty good sized peak at 85. So that's the, from 114 down to 85, that's the loss of 29 mass units. 29 is an ethyl radical. Does that make sense with our structure? Yes. Right here's a branching point. Here's a branching point, and you can lose an ethyl radical off. So the peak at 85, if we lose the ethyl radical off, then the cation would be right there where my finger is. So this peak at 85 is that cation. We lost an ethyl radical. Now, what this is telling us is, you know, if you're in the lab and you've made some